In section 4.4, we're looking at graphing functions, and we're going to look at some guidelines for creating a functions graph analytically and analyzing that functions graph. So this is also going to be similar to, you've got a project that you're going to work on in 4.4 as well, which is going to deal with many of these tasks. So we're going to deal with these both analytically by hand, and we're also going to graph them on the technology on Desmos. So the first thing we want to do is identify the domain or interval of interest. What functions should the function be graphed? And then our guidelines really start on the next page. This graphic just didn't fit all on the same page, unfortunately. And so there are the rest of the items. So here's what we really are looking at here for the things we want to find. We want to find the domain or interval of interest. They may not be the same, just depending on if the domain is restricted or if there is an interval that displays the graph better than others. So keep that in mind. You're going to want to talk about symmetry. When we talk about symmetry, we're talking about even functions and odd functions. The definition of an even function is that if you have the opposite x coordinate, f of x, f of negative x are going to be equal, so they have the same y coordinate. And then odd is, of course, that you have opposite x coordinates, you also have opposite y coordinates. So if it's even, odd, or neither, that'll give us some information about what the function might look like. Okay, the third thing that you're going to need is to find the first and second derivatives. That's because you're going to need to find the intervals of increase, decrease, the extrema, and so on. And so you use them to find the critical points and possible inflection points. So the critical points are our first order critical points. What they're calling possible inflection points in this box right here is what we have been calling the second order critical values. So second order critical points. And so what they call critical points right here is our first order critical points. So you just want to find both of those. And again, you're looking at all places where the derivative is both equal to 0 and fails to exist. Same thing for second derivative equals 0 or fails to exist. And then we're going to want to find the intervals in which the function is increasing / decreasing and concave up, concave down. So using our first derivative again and our second derivative. And so this is going to be the first derivative test. And the test for concavity. Then the next thing would be to use those tests to classify your extreme values and inflection points, if you have any. And then, so that's again the results of those two tests. And then moving on from the tests that we have that deal with those pieces, we're looking at where we have horizontal, vertical asymptotes and end behavior. And so those are going to deal with limits, things that we practiced in chapter 2. And then we're going to talk about intercepts. That's just some pre-calc stuff, or even algebra stuff, just talking about where the x-intercepts and y-intercepts are, and then finally making the graph. So we're going to do all of these things for a couple functions. We're going to look at one function right here in notes and you'll have a chance to explore it in 2 more in your project. Note, depending on the function, the precise order of these steps may vary. So that's a list of all the things I want to do. And so here's the function that we're going to do it with. It's a rational function. So in the first step, when I get into the domain or interval of interest, I'm going to look for places where the denominator is equal to 0, because that is going to give us excluded values not in the domain. So our denominator x squared minus 1 equals 0 gives us x equals plus and minus 1. And so that means that our domain is going to exclude those two values, so negative infinity up to 1, then negative 1 up to positive 1, and then 1 to infinity. That's just the interval notation if you prefer instead to write the set notation instead of all x, such that x is not equal to negative. I'll just use plus and minus 1 to shorthand that to negative 1 and positive 1. So set notation or interval notation for that domain. Okay. So we have our domain or our interval of interest. We're going to not graph, of course, to infinity, but we definitely want to look around the region where I have negative 1 to 1. I don't want to have it too far zoomed out because I really need to be able to see those places. So that's the first thing to think about when I get towards the graph. The domain helps me figure that out. And then we're going to talk about symmetry. So in symmetry, if I plug negative x into the function, that gives me, first of all, 10 times negative x to the third over negative x squared minus 1. So that's negative 10 times x cubed, because 3 negatives, of course, and then over x squared minus 1. That is the same thing as negative of the whole function, negative 10x cubed. You can factor that negative out. And so I do have the negative of f of x. So when I plugged in a negative x, I got out a negative y value, and so that means that I have odd symmetry. Okay, and when I have that odd symmetry, that means that I should visually, at least on the graph, see that I'm symmetric across the origin. Symmetric with respect to, I was putting just with there at first, so a little blurry there, but WRT for with respect to. So symmetric with respect to the origin. So even functions are symmetric with respect to the y-axis, and odd functions are symmetric with respect to the origin. Okay, so then the third thing that we need to find is the derivative, so the first and second derivative. So if I use the quotient rule to begin with this derivative, we'll have bottom, so x squared minus 1 times the derivative of the top, so 30x squared minus top, 10x cubed times the derivative of the bottom, 2x, over the bottom squared, x squared minus 1 squared. I'm going to get this simplified because I need to find its derivative. There's no way I would want to do that if it wasn't simplified. When you're using your project, you can type this version in just to make sure, but you have to simplify to get the second derivative anyway. So the second derivative, first of all, I'll simplify this. I've got 30x to the fourth minus 30x squared minus 20x to the fourth, there we go, over the x squared minus 1 squared, and if I combine like terms on that, I'm going to be having 10x to the fourth minus 30x squared, and then I have my x squared minus 1 squared. Okay, so that gives me my first derivative simplified. And then we're going to want to find the second derivative, and I can leave that one unsimplified, at least for the time being. So second derivative, bottom, so x squared minus 1 squared times the derivative of the top. So 40x to the third minus 60x minus top, 10x to the fourth minus 30x squared, times the derivative of the bottom. So I'm going to have to arrow that up. The derivative of the bottom is going to be 2 times x squared minus 1 to the first times 2x. So all of that right here times that line, and then all divided by bottom squared. Okay, I believe your project does ask you to leave things not simplified. If I go ahead, I'm going to simplify this one just so that we get some practice, and so also that we can solve a little easier for the critical values. First thing I would do is, since this large group and this large group have an x squared minus 1, is I would factor that out. So I have x squared minus 1 times, there's going to be a single x squared minus 1 left here, times the 40x cubed minus 60x, and then we'll have minus, and we have 4x times 10x to the fourth minus 30x squared over our x squared minus 1. Oops, I forgot to square it again. It was squared, so it's to the fourth power. So it was denominator, which was originally the second power, then to the second again makes it to the fourth power. Okay, now I am going to be able to reduce that because I have this one right here, cancels with one of those, gives me a third power there in the denominator. So we'll do that, and then we'll get some distributes going on up here to get this simplified. So we've got 40x to the fifth minus, close parenthesis there, minus 60x to the third minus 40x to the third plus 60x, then minus 40x to the fifth plus 120x to the third over our x squared minus 1 to the third, and continuing trying to get our like terms simplified here. We are going to subtract our 40x to the fifths, and then I have a negative 100x cubed right here and a positive 120x cubed, leaving us with 20x cubed plus that 60x over the x squared minus 1 to the third power. So that should be our second derivative simplified. All right, so now we have the third step done, and we're ready to go on to the fourth, which is finding those first order critical values and second order critical values. So step 4, let's get our first orders first. So we're going to find out where the first derivative is equal to 0 and where the first derivative fails to exist. Okay, first derivative equals 0. We have 10x to the fourth minus 30x squared over x squared minus 1 squared equals 0. Now, if I multiply the denominator over, I'm really just looking at the top equals 0. So I have 10x to the fourth minus 30x squared equals 0. And then I can factor that, factor out 10 and x squared gives us x squared minus 3 equals 0. So I have x squared equals 0, 10x squared technically, but the 10 divides off. So that gives me x equals 0, and then I have x squared equals 3. So x equals positive and negative square root of 3. Now for the first second, I wrote f double prime, I meant to write f single prime. I'm going to get to f double prime in a minute. So that's f single prime fails to exist. It's going to be places where the denominator is equal to 0, but that's going to be places where x squared equals 1, and so I have x equals plus and minus 1, but remember that your critical values have to be in the domain, and we had already said in step 1 that 1 and negative 1 were not in the domain, so these are not critical values. So these are not in the domain. That is one of the important reasons for finding the domain, is that if you find a critical value that looks like it's, if you find a candidate for a critical value, if it's not actually in the domain, it can't be a critical value. So I only have these 3 first order critical values. Okay, so we've got 3 first order criticals. Now we're going to find the second order criticals. Okay, second order criticals. This is where I take the second derivative now and set the second derivative equals to 0 and find out where the second derivative fails to exist. So first of all, second derivative equals 0. Second derivative is 20x to the third plus 60x over that x squared minus 1 to the third power. When it fails to exist, we're still having that denominator equals 0 piece, which gives us x equals plus and minus 1 again. And once again, I don't get any new candidates right here, so these are not in the domain still. And so I'm not going to have any second order critical values from the places where the second derivative fails to exist. I should get some from where it's equal to 0 though. Okay, so where it's equal to 0, that's the numerator equals 0, so I factor out 20x. We're going to be left with x squared plus 3 equals 0, and so we have x equals 0 and x squared equals negative 3, which would get me an imaginary unit, and so critical values can't be imaginary, of course, so they need to be real, so they're graphical, and so I only have 1, and so x equals 0 is our only second order critical value. All right, so we've got 1 second order critical value, and I had 3 first order critical values. That was step 4. Okay. Step 5 is going to have us use the first derivative test and the test for concavity to classify our critical values. So in step 5, if we're doing the first derivative test first, we're going to take the domain and we're going to partition it. So the domain, we're going to find those test intervals. We're going to pick some test values. I'm going to start a new video. This one's getting a little long.